Hey, Wheaton North, Mr. Igor here. This video is going to get into atomic structure and electron excitation, exciting electrons. Over time, our understanding of the atom has progressed quite a bit. We started as just thinking that an atom was just like a tiny little speck of sand, like a tiny little marble. J.J. Thomson, with his famous cathode ray tube experiment, discovered electrons, and so that kind of opened up the world to subatomic particles, which we didn't know existed prior to that. Rutherford, not too many years after that, came along and discovered the nucleus. So this is probably the most famous experiment in atomic theory history, the gold foil experiment, where he shoots the particles at gold foil, expects them to go through completely, but some of them bounce back at him. And this allowed him to say that the nucleus, there must be something in the center of the atom that's deflecting these particles. And so he discovered the nucleus, essentially. He didn't know much about how the electrons worked, and so soon after that, Bohr came along and said, the nucleus is there, but there's also these electrons that are orbiting the nucleus in very specific orbitals. They don't exist in between these orbitals, they only exist on these orbitals. And the further away from the nucleus, the higher the energy. And that's a very important point. I would underline that or star that, because we're going to come back to that. The further away from the nucleus, the higher the energy. About a decade later, de Broglie, Schrodinger, and Heisenberg, kind of over a period of time, this wasn't all this in the same year, but they kind of contributed bits and pieces to the understanding of the atom and electrons themselves, started describing electrons as more like a wave as opposed to a particle, and that these orbitals weren't really like these, specific orbitals like planets around the sun, but rather like regions of space around the nucleus, and they have different shapes and different energies. So it's consistent with Bohr, but kind of goes a little bit beyond Bohr, what Bohr said. Now, a little bit about the orbitals. We've seen this before, and so I won't spend too much time on this. Sodium, the two P's are not shown here, so let's go ahead and fill those in, the 1s2 and then 2s2 and then 2p6. Sodium would then be 3s1, right? And so we have the 1 arrow and the 3s. And the s orbitals are spherical. So we would have one electron kind of in that region of space, right, according to Schrodinger. If we move over to aluminum, we would fill that orbital, right? So now we have a second electron in that spherical region of space. But then we move on to the p orbitals. And the p orbitals have a different shape to them. They have this like dumbbell shape. And there's 3 orbitals, which explains why we can have up to 6 electrons, because each orbital holds 2 electrons. And they are in the x-axis, right, so kind of think horizontally. The y-axis would think vertically. And the z-axis, think like 3-dimensional, right, like kind of coming at you and then going back behind. So when we overlap them all, it kind of looks like this. And again, we would put 1 electron in each of those 3 orbitals before pairing those orbitals up, right? So aluminum would have 1 electron in one of those p orbitals. We just assume that it's the px. It's probably the case that it's not staying just in the px. It's probably there's a probability that it's also in the py or pz, but we don't need to get into that too much. Moving over to sulfur. Now we have the 4th element in the p block here. So we're going to spread out our electrons like this, and then we can pair them up, right? So now one of these 3 orbitals has 2 electrons in it, the other 2 only have 1. Moving on to chromium, so we would fill the 3 p's and then fill the 4 s's as well. And then notice this again, the 3d would fill after the 4s. It's a little bit higher in energy than the 4s, and we're filling from the lowest energy up. Okay. Now with the fourth element in that row, we would have 4 electrons, but we've talked about how chromium actually borrows one of those 4s electrons and puts it in the 3d. Moving on to zinc, then we would refill that 4s, right, and then we'd have 3d10. So when we put all of these in there, there's electrons in all of these orbitals kind of overlapping, right? So you can see like the inner s orbitals there, and then we have our p orbitals. And you'll see that the p orbitals are a little bit further from the nucleus on average, and so that means they're a little bit higher in energy. All right, now what do I mean by energy? Because we're using this term energy, and it's kind of difficult to wrap our heads around this a little bit. Let's understand this by analogy, or use an analogy to help us understand it. Picture yourself in a ditch, and you're going to kick a soccer ball, right? Only a specific quantity of energy can get the ball out of the ditch. If you kick it with less than that amount of energy, it's going to fall back down to you. So if you kick it to here, it's going to fall back down. If you kick it to here, it's going to fall back down. Only if you get a certain amount of energy are you going to get it out of the ditch, right? And it's at lowest potential energy where? It's at lowest potential energy when it's in the bottom of the ditch. The deepest it can get is the lowest potential energy. If you kick it up to here, now it has higher potential energy. You've had to input energy into the ball to get it up that high, right? It will naturally fall back down to the lowest energy. Now this is, by analogy, similar to what's happening in the atom. Think of this as our ditch, right? Where the nucleus is pulling electrons towards itself, right? And the closer you are to the nucleus, the stronger that attraction force, and it would require energy to go up in the ditch, right? So let's look at this picture here. This electron is pulled towards the nucleus. It would require an input of energy to get it to move away from the nucleus, right? Because there's an attraction force to the nucleus. Now, how do we get it to move up in energy levels? We can excite it with energy, usually from photons or light. So if light comes in and the atom absorbs the energy, if it's the right quantity of energy, the electron will jump away from the nucleus, right, because of that input in energy, and to an excited state. So we call this like the ground state, and we would call this the excited state. Here's another example that kind of shows this. Here's our ground state, right, the lowest possible it could be, and we're thinking of hydrogen in this case. So electrons can jump up by absorbing energy in the form of light, and they release that same amount of energy when they come back to the ground state, okay? So notice this, energy absorbed makes it go up in energy, right? Energy emitted or released makes it go down in energy. And that same amount of energy is absorbed and then released, okay? Because it's a very specific quantities. This energy level and this energy level are at very specific quantities. I really like this picture because it shows the potential energy, right? Notice how deep in the well the first energy level is. It takes 1,000 kilojoules per mole to get it to go up to the second energy level. Once you get further from the nucleus, then it takes less and less energy to go to every subsequent energy level. But I'm trying to really drive this point home that closer to the nucleus is low and negative potential energy. This is referred to as an electron emission spectrum of hydrogen. Because these are very specific quantities, they're even calculated here. A transition from like 6 to 2, for example, gives off a very specific amount of energy, and therefore a very specific wavelength, even down to 1/10 of a nanometer. And so it's going to give off a very specific color of light. This energy can actually be calculated. This is called the Rydstad equation, and R is a Rydstad constant. H is Planck's constant. C is the speed of light. So these are all constants, and so it calculates out to 2.18 times 10 to the negative 18 joules. And then N is the energy level. So you can find a difference between two energy levels by just subtracting the two quantities of energy. This is essentially showing the same thing, but what I like about this is that it gets to 0 joules. You're at negative potential energy here because you're really low and deep in that well. It requires an input of energy to get you up, and if you can get out and past that last energy level, so excitation would be to go from like here to here, and then it would go back down. It would fall back down to its ground state on its own, the electron would. If we can get it past even the furthest out energy level, then that's ionization, right? Now you've lost the electron completely if you've gotten it past that threshold. So a certain quantity will take it from 1 to 2, or from 1 to 3, or from 3 to 5, and so on. But if you put in enough energy, eventually you can get the electron to completely leave the atom, and that would be ionization, right? Excitation is just moving within the atom. Ionization would be to remove the electron completely. So we've covered a lot of ground now. Hopefully you understand the difference between electrons getting excited versus ionization, and you're comfortable with orbital shapes and orbital filling diagrams and kind of the overall structure of the atom. If you have any questions, write those down as always. Bring them to class. And this is Mr. Yergler signing off.